let's suppose you have two floating point numbers, x and y, and we want to add them together. Well, we're going to assume that when you do that operation, right, you have to get another floating point number, and that floating point result of adding x and y is, again, relatively close to the true result. So what this means, remember, is a relative error of size epsilon in the result x plus y. And that epsilon has to be less than or equal to machine epsilon. So this is, except for some very fine-grained details, this is provably true for every modern processor. So it's really not a bad assumption to make at all. And what this means is that everything that we do with a floating point number, including representing real numbers and then adding real numbers, the same goes for subtraction, multiplication, division. We can more or less assume the same kind of thing about square roots and all the elementary functions, if you like. They all introduce some relative error which is bounded by machine epsilon. So, for example, suppose x and y were real numbers. Well, first we have to represent them as floating points. So floating point x is some small perturbation of x, and the floating point value of y is some other small perturbation of y. I can't assume that epsilon 1 and epsilon 2 are the same. It's different for every value. But I do know that epsilon 1 and epsilon 2 are both less than or equal to machine epsilon. Now, if I want to add those two values together, right, the result of adding the floating points values together by our assumption above is equal to some other, yet a third small perturbation of the true result for the floating point values. So now we have to substitute those in. We get 1 plus epsilon 3 times 1 plus epsilon 1x plus 1 plus epsilon 2y. Now we have to start doing some rearranging. There is an x plus y in there somewhere. There is an epsilon 1x plus epsilon 2y. And then there's all of that again times epsilon 3. Okay, let me create a little bit more space here. Oops. Okay, so continuing, let's, x plus y is the thing that we were trying to find, remember, ideally. And then the perturbation to that result, I'll gather everything that multiplies x. So I have an epsilon 1 plus epsilon 3 plus epsilon 1 times epsilon 3. And then times y, we have epsilon 2 plus epsilon 3 plus epsilon 2 epsilon 3 times y. Okay, so now if we wanted to get into the details of the mathematics, well, epsilon 1 and epsilon 2 and epsilon 3, I forgot to state up here that epsilon 3 is also required to be less than epsilon machine. So those are all really small numbers, and their product is really, really small, sort of doubly small. So we would just sort of neglect those, right? And we could show, more or less, that these two values are bounded by 2 times epsilon m, and these two values are bounded by 2 times epsilon m, and so the whole thing is close to x plus y times a small multiple of machine epsilon, times the x and the y themselves. Okay, so as you can see, even for a really minor calculation, this is a big pain, and this kind of analysis actually isn't done very often. We could simulate it experimentally, which is often useful, So here's an example of how we might go about that. So in MATLAB, I would set up, I'm going to set things up so that I can see all the digits, and I'm going to create a polynomial. So this command poly creates a polynomial whose roots are the given values. So x minus 2.5 times x plus 1.25. That's going to define our p of x. So quadratic polynomial with known roots. Well, if you multiply all that out, right, the coefficient of x squared is 1. The coefficient of x is minus 1.25, right? So this multiplies x squared, this multiplies x, and then this number multiplies the 1 in the polynomial. This is how MATLAB always represents polynomials, as a vector of coefficients from the highest degree down to the lowest. All right? Now, if we're going to simulate this in the machine, we're going to have to use a larger value of machine epsilon than the native one. And so what we're going to do here is simulate 6 significant digits. Okay, and how we do that is then we introduce a relative perturbation, okay, in each coefficient. So here's the size of our perturbation. So rand is a built-in function which returns a random number between 0 and 1. Okay, so I have 3 random numbers, 1 for each coefficient of p. Those random numbers I then subtract 1/2 so that they lie between minus 1/2 and 1/2. And then I multiply by 2. So altogether, right, this part gives me a random value in the interval minus 1, 1. And then I just scale those by machine epsilon. So I have 3 values of epsilon that are less than 10 to the minus 6. So I take each coefficient of p and I want to perturb it by, or multiply it by 1 plus epsilon, 1 plus its own private value of epsilon. Remember, the dot star does element-wise multiplication. Okay? So in other words, we get p of 1 times 1 plus epsilon of 1, and then we get p of 2 times 1 plus epsilon 2, and so on. So here are my perturbed coefficients. You see that they're perturbed past 6 significant digits, just as they would be in our computer that has 6 correct significant digits. Then I'll use MATLAB's command roots to find the roots of that polynomial. So I'm cheating here a little bit, as I'll explain in a second. But you see that the answers are pretty close to 2.5 exactly, and minus 1.25, which we know to be the exact roots of the original polynomial. And in fact, if you rounded them off to 6 significant digits, keeping in mind what the first admitted digit is, you would get exactly those results, to 6 digits. And when I say I'm cheating, what I mean is I'm doing a partial experiment. I've perturbed the data to the problem. I've perturbed the polynomial coefficients, but I didn't perturb the arithmetic. The arithmetic is still the native double precision arithmetic. So if I wanted to explore what the algorithm of roots was doing, I'd have to go into it and step by step for each arithmetic operation introduce rounding errors scaled up to size 10 to the minus 6. So you can do these experiments, but even they're relatively straightforward but tedious to do. So here's a case where everything worked out nicely. Okay, the perturbation in the answer was essentially the same size as the perturbation in the data, and that makes us pretty happy. But in fact, we can't expect that all the time, and there's a relatively simple example to say why. So if we take the internal representation of pi, okay, it's accurate to about 16 significant digits. Then there's a rational number approximation that's better than 22 over 7. I'm going to subtract this number from pi, so I'll make it negative. And you see it agrees with pi to about 1, 2, 3, 4, 5, 6, 7, right? Well, that means that when I take alpha and add x, right, these digits cancel each other out. And the error starts in the 7th decimal place. Well, there's a problem, right? Because I know that I started with this many accurate digits, right, plus the ones that got canceled out. So there's no way I could hope to get more than 1, 2, 3, 4, 5, 6, 7, 8, 9 digits left. In other words, yes, the number is represented still to 16 significant digits, but I know that at least, or perhaps as many as 7 of them are utter garbage. They can't possibly be correct because the original computation didn't even know pi to more digits than that. This is a phenomenon known as cancellation error. Whenever you subtract 2 nearby values to get a much smaller result, smaller in magnitude, you get this kind of cancellation effect. Another way of looking at it is that this result is accurate relative to x and alpha, but not to itself. So accurate relative to the data, but not to the answer. And cancellation is bad news. We want to avoid it whenever possible. And what we're going to do next is talk about the difference between cases where it's unavoidable and cases where it's avoidable.